Hello, today we're going to look at assignment 13 of the STEP support programme. This is a graph sketching question, which has got 3 parts. They're all linked to the previous part. So the first one's got an x to the power 4 minus 6x squared plus b. Then we change to ax plus b. And then for the last part, we've just got an ax. We haven't got the b going on. Let's start by looking at the first part. So the first part starts by asking us to sketch the graph y equals x to the power 4 minus 6x squared plus 9, giving the coordinates of the stationary points. Before I start thinking about the stationary points, I'm going to look at where it crosses the axes. So where it crosses the y-axis, we know that x equals 0. This will give me y equals 0 minus 0 plus 9, gives me y equals 9. Where it crosses the x-axis, we know y equals 0. So that gives me x to the power 4 minus 6x squared plus 9 equals 0. This is actually a perfect square, so I can write this as x squared minus 3 all squared equals 0. This tells me that x is plus or minus the square root of 3. So I now know it goes to the points 0, 9 and plus or minus root 3, 0. So those are the points where it crosses the axes. Now for the stationary points, we can differentiate. So this gives me 4x cubed minus 12x, and the 9 goes to 0. I can factorize out of 4x, and we want this to equal 0 for the stationary points. So here I have x equals 0, and here I have x equals plus or minus root 3. So these points here are also the stationary points. Okay, so let's sketch the graph. You can, if you like, find the second derivative and work out for sure which of these are maximum and which of these are minimums. You don't actually need to do that because you know, since you have an x to the power 4, you know you've got to be really big here and really big here. You know it's going to be symmetrical about the y-axis, and you also know that 0.9 is going to be higher. So 0.9, say, is there. It's going to be higher than 0. So we've got 0.9 here, minus root 3 here, plus root 3 here. So the only way we can do this is to have something that looks a little bit like a Mexican hat. I'm going to just get rid of these 2 drawings here. And so your graph is going to look something like this. It's quite steep at the top, but it will do. Okay, and you can write, if you like, symmetrical about the y-axis. Anytime you're drawing a graph and you think you haven't got it quite right, just at the side write a note saying symmetrical about the y-axis, or whatever it is that you feel you haven't quite drawn exactly. Okay, let's have a look at the next part of the question. So I'm going to get rid of this working, so I've got some space to do things. Takes a little bit of a while to delete things if you don't want to delete everything. There we go. Okay, this case here is the case when b equals 9. We've got y equals x to the power 4 minus 6x squared plus 9. And when this equals 0, we've got 2 places where this equals 0, here and here. So we've got 2, and I'm going to call them roots. That's basically equations of this equals 0. If b was a little bit higher, our graph would change slightly. So if b equaled 10, and we were looking at the graph of y equals x to the power 4 minus 6x squared plus 10, well, this is the same as x to the power 4 minus 6x squared plus 9 plus 1, which is the same as this blue graph here, just shifted up 1. Okay, so this would be b equals 10. And you can see from this, there's no places where this crosses the x-axis. So here we have 0 roots. Okay, let's take a slightly smaller value of b. So if we say took b equals 8, then this would go down by 1. And you can see, it's not a brilliant picture, but when b equals 8, we've gone from 2 roots to 4 roots. Okay, so as b decreases, you're going to keep 4 roots until you get to the point where this peak of the Mexican hat here goes to the origin. So until you get to the point that looks a bit like this, when you're going to get 3 roots. So this point here has gone down by 9. So this is the point where we've got plus 0. This is the point b equals 0, and we've got 3 roots. And then as b gets lower, that peak of the Mexican hat is going to lie underneath the x-axis. So for anything smaller, you're going to get just the 2 roots. I haven't quite drawn my x-axis long enough. Okay, so let's go through the question parts here in order. So n equals 0 when there are no roots. That's the case when I've got my b bigger than 9. So it's like the red case. So when nothing actually crosses the x-axis. When n equals 1, I don't think there's any case where I can just get 1 roots. I go from 0 roots to 2 roots to 4 roots to 3 roots for just one value b back to 2 roots. So for n equals 1, there are no values of b. For n equals 2, we've got the sort of edge case when b equals 9. And we've also got when b is negative. So when b equals 9 or when b is less than 0, we have 2 roots. We have 3 roots at just one particular case, and that's when this peak has hit the origin. So that's when b equals 0. And we have 4 roots for anything that looks a bit like the green line. So when b is between 9 up here and 0 down here. So it's a good idea just to check we've covered all values of b and that we haven't double counted. So we've got when b is negative, n equals 2. When b equals 0 exactly, n equals 3. For b between 0 and 9, n equals 4. b equals 9 exactly, n equals 2. And b bigger than 9, n equals 0. So we've covered all the possible values of b and we haven't double counted any. Okay, so that's the first part of the question. So let's go on to the second part. Okay, so for this part, it starts by asking us for which values of a does this curve have a point at where these are both equal to 0. So let's differentiate once. This will give me 4x cubed plus 12x, no, not plus, minus, a bit like before. And then we also get a plus a from this ax term, and the b goes to 0. That's a cubic. I want that to equal 0, but let's have a look at the quadratic. Let's have a look at the second derivative. The reason I'm doing for this is that's going to get rid of a. So the second derivative gives me 12x squared minus 12 equals 0. So if I factorize out to 12, I get x squared minus 1 equals 0. And so x equals plus or minus 1. So we now know 2 values of x for which the second derivative is 0. If we plug these back into dy by dx, so when x equals 1, we get 4 here, minus 12 from the minus 12x, plus a equals 0. This gives me a equals 8. When x equals minus 1, we get minus 4 from 4x cubed, plus 12 from 12x, plus a equals 0. That gives me a equals minus 8. Okay, so I'm just going to clear those drawings and then write that out again. So when x equals 1 is the point, then a equals 8. And if x equals minus 1, then a equals minus 8. So those are the 2 different values. Okay, now we're trying to find the number of roots of this equation. And it's a good idea to think about maybe doing something like we did before. Let's take a equals 8. And let's have a look at the graph y equals x to the 4 minus 6x squared plus 8x. So it looks a bit like this. I've taken b equals 0 for now. Okay, so in a similar way before, we know that when x equals 0, y equals 0. We know that when y equals 0, we've got x to the power 4 minus 6x squared plus 8x equals 0. X into x cubed minus 6x plus 8 equals 0. This is a cubic. Let's not worry too much about solving that cubic for now. If I differentiate, so if I want to look at the where I've got stationary points, then I'm going to get dy by dx is equal to 4x cubed minus 12x plus 8 equals 0. I can divide by 4. 2x cubed minus 6x plus, divide by 4 gives me 1 there. Let's try that again. X cubed plus, divide by 4 minus 3x plus 2 equals 0. Okay, I already know that I'm taking a equals 8, so I already know that x equals 1 has got to be one of these points. So I can factorize out an x minus 1. Then I'd have to have an x squared, so that I get x cubed. This gives me a minus x squared, so I'll need to plus on an x. So I'll get a plus x squared as well. I've got a minus x. Well, I want a plus 2 here, so this is going to have to be minus 2. So that becomes plus 2. And just to check the x term, minus 1 times x minus 2 times x gives me minus 3x. So I'm pretty sure I've factorized that correctly. And then if I try and factorize this bracket as well, I'm going to get x minus 1. Here, this is the same as x plus 2, x minus 1. So I know that dy by dx equals 0. Let's actually write this up here where we've got some room. Dy by dx equals 0 for x equals 1 and x equals minus 2. So let's see if we've got enough to start drawing this picture yet. So I know that it goes to the point 0, 0. I know that I have a stationary point when x equals minus 1. And that's also a point where the second derivative is equal to 0. And I know I have a stationary point when x equals minus 2. It might be a good idea to stick those points into my equation and find out what the y coordinates are. So, oops, didn't mean to get rid of the y. Let's just get rid of some of this working. You wouldn't delete all your working, you would just leave it there. It's just I want to keep everything onto the same screen. And I don't have a very big screen for doing this. There we go. Okay, so let's put my y back in. Okay, so if x equals 1, y is equal to 1 minus 6 plus 8. That equals 3. So I know I've got the point 1, 3. Let's say that's about there-ish. And when x equals minus 2, I get minus 2 to the power 4. That's 16. Minus 6 times, okay, minus 2 squared is 4. Plus 8 times minus 2. That is 16. Minus 6 times 4 is 24. 8 times minus 2 is minus 16. So I get minus 24. So I think my x equals minus 2, minus 24. I just need to remove those brackets which are getting in my way. I've got a point down here which is at minus 2, minus 24. Okay, I know that I've got to end up really big and positive when x is really big and negative. And I know I've got to end up really big and positive when x is big and positive. So essentially, this point here could either be a point of inflection, but that would mean that I end up keep going downwards and there's no way I can hit that point, or this point would have to be a minimum. And that's actually the point it has to be. There's no actual other way, any other way to draw this graph. So that's supposed to be a point of inflection. That could actually be slightly better than that. Okay, what I'll do, I'm just going to get rid of that point and I'll mark it in afterwards. Okay, so we've got to go through that point, through the origin, got to have a point of inflection, and then up and away. Okay, so we'll call that the point 1, 3. Not very much to scale, and this is when b equals 0. So you can see here that when b equals 0, we've got 2 roots. Okay, so as b gets bigger, we're going to keep ending up with 2 roots until we get to the point where this hits the x-axis, which is going to look like this. And that's going to be when b equals 24. Oops, you might not be able to see that because of the video. So that's gone up by 24. As it starts going downwards, we're going to keep having 2 roots everywhere. We might end up at a point where we've actually got the point of inflection on this line, but that doesn't matter. That's still 2 roots. So something like this. So that's when b equals -3, because it's gone down 3, still has 2 roots. Okay, so the cases here are, just clear some space. So when b is bigger than 24, we have no roots. So that's higher than that red line. When b equals 24, we have 1 root. When b is less than 24, we have 2 roots. And we're always going to have 2 roots as b gets even less than 24. Okay, so that was when a equaled 8. Now let's consider the case when a equals -8. And I'm going to do a bit of a trick here. So if we let f of x equal x to the power 4 minus 6x squared plus 8x, which is the graph that we've just done here. So this is f of x, if you like. F of minus x, so that's what you get if you reflect it in the y-axis. That is equal to x to the power 4, because that's a negative, and the negative to the power 4 gives a positive, minus 6x squared minus 8x. So the graph when a equals -8 looks exactly the same, apart from the fact it's been reflected. So we all get this graph. So this is x to the power 4 minus 6x squared minus 8x. And so you'll get exactly the same situation when a equals -8 as you had when a equals 8. So actually, we don't need to do any more work here now, apart from to say that's for both a equals 8 and a equals -8. We have that situation. Okay, so that's that part of the question done. So let's have a look at the last part. Okay, so for the last part, we want to sketch one curve when a is bigger than 8. So let's start thinking again. We have got y, let's start by differentiating. Y by dx is, so especially since we did lots of talking about stationary points before. So this is my dy by dx, okay? We can look to see, we can have a look to see what happens for the second derivative as well. We know that when, in a similar way to before, d squared y by dx squared is equal to 12x squared minus 12. So we have, this is equal to 0 when x equals 1 or -1, okay? So there are a couple of things we could do. We could either start sketching what the gradient would look like, and then we can try and work out what the function looks like, or we can keep going with what we've got. So let's start by thinking about this. So when a is bigger than 8, then when x equals 1, dy by dx is equal to 4 minus 12 plus 8 is going to be bigger than 0. Okay, and then as x gets bigger than 1, that's going to keep increasing. Let's start drawing some axes over here with some stuff that we know. What else do we know? So I think it might be quite a nice idea actually to sketch the gradient. So if we consider dy by dx, and we're going to sketch this. Right, we know that dy by dx is a cubic. We know it's got stationary values when x equals 1. When x equals 1, dy by dx is equal to 4 minus 12 plus a, so that's equal to a minus 8. And then when x equals minus 1, we've got dy by dx is equal to, so minus 4 plus 8 plus a, so that equals a plus 8. So for those 2 points, we know that, so we've got minus 1 a plus 8 and plus 1 a minus 8. When x equals 0, this goes through a. So my gradient function, it's a cubic, is going to look something like this. So this is dy by dx. Okay, and we know that a is bigger than 8. Let's try and use that gradient function to help us sketch the other graph. So at this point here, my graph y is going to have a stationary point. And we know that at this point, the gradient is increasing. We don't know it's increasing. We know that the gradient is going from negative to positive. So we're going to have a stationary point, and it's probably going to be something like this. So gradient is negative. We're going to have a stationary point at about here. Then the gradient is going to increase. We're going to have maximum gradient here, and then it's going to start to decrease again. And we're going to get a 0 gradient again here. So we're going to get a sort of slight point of inflection. I've done this a bit badly wrong. I'm going to just try this again. I'll tell you why I've done this wrong. That's because the gradient is always positive. Sometimes these questions do go slightly wrong. Okay, so thinking about my dy by dx gradient, this is a cubic. We know that when x equals 1, dy by dx is a minus 8. When x equals minus 1, dy by dx is a plus 8. So we're going to get a gradient which is minus 1, a plus 8, goes to a minus 8. But because a is bigger than 8, my gradient is always positive. So that's my dy by dx graph. Okay, so now if we try and consider what y looks like, we know that in this region of the graph down here, the gradient is negative. Let's just make this a bit bigger. Okay, so in this region of the graph down here, the gradient is negative. Then here the gradient becomes positive, and it stays positive throughout the rest of the graph. I also know that when x equals 0, y equals 0. So I know we go through that point here. I know in this region the gradient is negative, and then for the rest of the graph the gradient is positive. I know that the gradient is positive, but the increase in the gradient is decreasing up to this point. So I get what's called a non-stationary point of inflection here. So that's where the bend of the curve changes. And here I know the gradient is 0, So down here, I'm going to get a stationary point, a bit like that. So what's a really good idea to do now is to go away with this question and try and sketch some graphs on a graphic calculator or on Desmos or something. On Desmos, you can use a slider which shows you how this whole graph changes as A changes. Okay, well, thank you very much.